Hope you can hear me well.
Yes, we can
Okay,
hear.
I'll get started. I
Yeah,
think
go
on
ahead. Thank
YouTube
you.
I can see that I'm streaming, and I'll hopefully also be audible. Yeah, I'm very sad that I can't be with you in Singapore, and I'm also very sorry that you now have to sit through a remote talk just after lunch break. I know it can be hard to pay attention to a talk delivered remotely, so I'll try to lighten things up a bit. By having some pictures somewhere along the line. But let's get started. In this talk, as Dominic already said, it's going to be about linear types. And linear types are inspired by linear logic. If you haven't come across linear logic, in a nutshell, it's a restriction of classical logic where we treat variables as resources and we can't just duplicate or discard resources freely. So in linear logic, these two functions are actually not tautologies. So we write this OX or tensor for AND in linear logic. So A and B does in fact not imply A. So this lollipop symbol here is the implication of linear logic. And similarly, we can't just copy the given A. So we don't have a function taking A to A and A. And linear logic is very useful in programming because if we, under the propositions as types interpretation, look at programs in a linear type system, then they have to be tautologies of linear logic, which in the case of a function between two lists means that any function, any linear function of this type, has to be in fact just permuting the list because we can't drop any elements of this list or we can't duplicate any elements in this list. And hence, we already have actually a quite strong property satisfied if this is a program in a linear type system. If you've ever shown a sorting algorithm correct, I think you know that it's quite tricky, or the trickiest part is actually to show precisely this, that your sorting function is just a permutation. So this comes for free as a specification in a linear type system. A very natural extension then to linear logic is to still allow in a restricted way copying if we explicitly annotate it. So there's this idea of introducing a multiplicity, which will, kind of in the spirit of linear logic, ensure that, or like a type system will ensure that any program where a variable has a given multiplicity, this variable is used exactly as many times as the multiplicity says. So for instance, if we have here the copying function, we can indeed, we will want to have a copying function in our functional programs, and we can indeed implement this if we say, yeah, we're actually using 2 times this variable. So this has been a very fruitful idea that has been implemented in several different systems. Beatrice is one of them based on quantitative type theory, granular linear Haskell. So that's quite neat because it kind of gives us for free specifications. There's a catch, however, because quite often it's not possible to determine a static multiplicity. Consider this program, which is a program which attempts to extract the head of a given list axis. And in case the list is empty, we'll use a backup element y. And then we'll spit out kind of the head of the list or a y, as well as the rest of the list. For this to be a linear program, we also have to kind of give back the rest that we didn't use actually. So our safe head program is just defined by pattern matching, and in case we are given the empty list, then we'll use the y, and we don't have any remaining elements. And in case we actually have something in our list, then we don't even look at the y, right? So in this case, we don't need y, so the multiplicity of y can be really 0 or 1. It depends on the given list. So this is something that we can't capture in systems with static multiplicities. So the point of this talk will be to introduce a way to add dynamic multiplicities, so to give a typing discipline where we can give a precise type to the safe head function. And moreover, we don't even have to cook up a new system because we can add this to an existing dependent type theory. We'll use cubical acta because it has some nice features, but it's actually not crucial to use cubical acta. So we can really carry out this construction in any dependent type theory, and nothing that I'll show you in the following is a postulate or an axiom or anything like this. This is all kind of just cubical acta programming, and it's actually inspired by Gödel's dialectica construction, which if you haven't heard about it, don't worry about it. But in a nutshell, dialectica is a kind of recipe to turn an intuitionistic calculus into a linear one. That might be one way to characterize it. So here, Kurt Gödel is depicted pulling out the rabbit out of the hat. So it's a very neat trick that we can employ whenever we need to kind of linearize a calculus in some way. All right, let's make this concrete. So we will make use of cubical acta, and particularly we'll make use of bags or finite multisets, as they're also often sometimes called. And they are in essence just lists where we don't care about the ordering of the elements in the list. So we kind of have, again, a nil constructor for a bag. We have a cons operator, which allows us to put something in front of a bag. We have an append operator, which is just plus in Haskell, but we've suggestively chosen already the tensor symbol here for the append operator. And crucially, because we kind of quotient these lists by reordering, this also means that this tensor operation is commutative. So that's some nice symmetry that already suggests that we can use this for something of some linear logic hacking. And we'll just use these bags that are provided by cubical acta and define the type of supplies, which are just kind of the maximally polymorphic bags in some way. So any value can be put into a supply because we just use this sigma type here. If you haven't seen dependent type theory yet, don't worry about it. We'll just use, I think, 2 sigma types. And the first one is this, which just says, well, really, in a bag, we can put a pair of a type and then an inhabitant of this type. So for instance, this iota allows us for any type A to take an element A and produce a supply. So we'll just put an A comma A in front of the empty supply. And actually, you don't really need to worry about the implementation details of supplies in the following. What matters is that we have this iota, which allows us to turn anything into a supply. So if we have, for instance, iota x for some x of type A, and we also have the iota axis, where axis is a different type from x. It's a list of a's, but we can pack both things into the same supply. And we will only pretty much use the diamond symbol for the empty supply, the tensor symbol, and the iota in the following. So this is kind of all you need to remember from this slide. And the reason we introduce these supplies is that we think of these as kind of the contexts that tell us which resources we can use in a construction. Crucially, they're not contexts, right? They're just some terms living in this supply type, and they do not contain just variables, right? But rather they kind of may repeat variables from the host-dependent type theory, but they can contain any kinds of things. But really, kind of what we care about is what variables the supply tells us that we're allowed to use. Okay, so the supplies are the first ingredient that we need. The second one are what we could call productions, which kind of turn one supply into another. So the bag of cubical acta already has some nice structure. For instance, we said we can just reorder things in a supply. In particular, this means we don't care whether we have an x and an axis or an axis and an x in a different order given into a supply. But we'll also often encounter cases where a supply contains actually an x and an axis put together into a list. So this double colon here is the normal list cons operator. So if we really put x in front of axis and then consider this as a supply, this morally has the same resources as, well, either of these two supplies, right? But this is something we won't be able to prove. I mean, actually, this won't be false, because if you had a length function for supplies, the length of the supply is 2, the length of this is only 1. So this certainly can't be equal to either of these two sides. So we have to kind of introduce a slightly different notion of sameness. And for this purpose, we have these productions. So they're really a relation between supplies. And kind of they inherit the properties of equality. Actually, like most of the productions, you can write down relatively quickly if you're familiar with the categorical semantics of linear logic. So kind of for the experts, you can think of the supplies as the object of a symmetric monodic category, and then the productions are morphisms between these objects. If you haven't heard about the categorical semantics, don't worry. The crucial point being is kind of most of them are actually not very surprising. The only thing that we kind of have to add, which is not maybe obvious, is that we will want to be able to add and remove constructor symbols freely. So I said above, well, morally, this supply here on the right-hand side should be the same as on the left-hand side. Let's capture this with a production. So here this OPL cons, oplux, I'll read it as oplux, says that iota of x in front of x's can be turned into x and then the x's separately in the supply. And we can also go in the other direction with the lux cons production. And we also actually are allowed to just discard the empty list because it doesn't contain any resources. So we have this oplux empty list production, which turns iota empty list into the diamond and vice versa. And again, there's a kind of nice categorical structure that justifies these productions, namely that iota is strong monoidal with respect to products, but we don't need to worry about this. We just need to remember that we now have supplies and productions, and this is all the structure that we had to add to now be able to talk about linearity in cubical acta. And we'll do this by looking at this following dependent type, which is just something that we kind of write down exactly like this in cubical acta. So it's just a definition, which we read as a sort of linear judgment. So like we read this as in the supply, which is kind of a linear context delta, we can derive something of type A using the rules of linear logic. So this is why this entailment symbol is written this way. Precisely if, again, a sigma type, where the first element of the sigma type will be an inhabitant of A. So if we can actually produce something of type A, and also we can produce a production which witnesses that delta contains exactly the resources of A. So kind of we have to do two things, just construct the intuitionistic term, and then also show that this term is really made up of the resources that we're given. And that's kind of the crucial definition. And thereby we can already talk about linearity in cubical acta. So kind of these two constructions, supplies and productions, and then this dependent type. And now we have everything we need. For instance, we can type our safe head function, which, as you remembered, took in a list x's and an element y. And now we construct something of this linear entailment type. So this here on the left-hand side is the supply that we are looking at. And then on the right-hand side, we have the output type that we try to construct. So we want to construct a pair of an A and a list of A's. And the supply is now actually performing some computation, right? Because it's just something that lives inside the type theory. We can in particular just use functions such as this null function, which will just give us back a Boolean, checking whether the axis is null. And we can represent this dependency between x's and y now in our supply. We can just say, well, we'll need this y only in case our axis is null, otherwise just give back the diamond symbol. We will certainly need the axis though. And then if we implement this safe head program, since this is a sigma type, this linear entailment, we really have to give two things. First of all, a witness of A cross list A. So this is the same one as before. So we'll just give back Y in the first case, X in the second case as the remainder of the list here. And the second thing we have to do is now to provide a witness that we've actually used the given resources, right? So we have to construct this production. And now it's very convenient that cubical acta reduces things appropriately for us. So for instance, in the first case, null axis will reduce to true, which means this will actually, this whole if and else expression will reduce to iota y. So we have something which is almost looking like the supply we have actually available. And similarly, in the second case, where actually this diamond will also be discarded because this OX is implemented in with computational contact in cubical acta. So this almost looks like we have used the provided resources. We just need to provide some witnesses of this production data type, which aren't super interesting. So we just need to compose some lux, some oplux productions for the different data types, which aren't very interesting. So mostly I will skip these, but it's usually quite straightforward to come up with these. Okay, so this was the construction. Now let's do some hacking with it. So this is Kurt Gödel depicted how he might have looked like if he had lived 100 years later. And his immense power is apparent by the fact that he's able to look through the screen and code. And maybe this would be the kind of programs that he would have written, because we're now using this dialectical construction in cubical actor to program. We've already actually seen something quite cool with the save head function. Let me go back, because we've deconstructed this axis here, right, to produce something. So we've kind of used an elimination principle for axis, an elimination principle which treated this list appropriately as a resource. And we can generalize this to derive linear elimination principles. So we didn't have to talk about linear elimination at all, right? When we set up our theory, we only talked about constructor symbols, but it turns out actually we get these linear elimination principles for free. So let's introduce this abbreviation, that these aren't really linear functions from A to B. They're kind of just working in a similar way. They're really dependent functions which take an A to a witness that X can be turned into B linearly. But these kind of work like functions. So we can, for instance, apply these with at, and then we can implement a fold principle for lists, which is a linear fold principle, because we're now giving a const function which is linear, so it takes an A and a B, uses both to produce a B. It has a nil case, which just has a B being produced from a delta. And then the linear fold principle, or actually a linear fold principle, this is why there's a 1 here. There's in general many sensible elimination principles you can give in a linear setting. A linear elimination principle would turn any list, and using this list once, as well as the delta, which is needed for the base case, into a B. And we can just define this fold R1 by pattern matching, or actually dependent elimination is what's at the core here, using kind of our add function, and there's like some syntactic sugar that is needed to like kind of lift everything from an intuitionistic level into our linear level. But crucially, kind of this works just in the way you would expect a fold to work. And this requires some work, like this by ... means we had to apply some production, so there's some bookworking that needs to be done. But we can use this fold on functions such as a linear insert, and this gives us a insertion sort, which we know will not drop or duplicate any elements because it's in this linear system. And it's defined in exactly the way you would expect. It's just a fold of insert on the empty list, where again, this is kind of the empty list considered linearly. So we don't have to do any more work. So I think this is quite neat. And yeah, I think what is nice from a theoretical point of view is that we didn't have to like think about data types linearly, really, because they kind of can be treated linearly just by using dependent elimination. Okay, the second thing I wanted to mention is that we now can also really cash in on the fact that we can compute in our supplies by introducing something which looks really like multiplicities in other systems, where we don't have to add any more structure, but we can just use the built-in natural numbers of ACTA to draw multiplicities from. So we don't have to impose an additional semi-ring on the structured rules or anything like this, because we work in this ambient type theory, can just use this type theory to compute resources for us as well. So, for instance, we can cook up a fold R2, so a different kind of folding principle for lists, which has a slightly more involved const case, where crucially in the const case, we make use of a delta 1 supply. So in each step that we're folding our list, we will need to have we are using some supply delta 1, which means we'll need this delta 1 as many times as our list has elements, right? So this is why this exponentiation function here was introduced, which is, again, just kind of an inductive definition in the host-dependent type theory. Like there's nothing fancy going on. It's really just taking n copies of a given supply delta. And we can use this here to give a precise type to this linear fold for lists. Namely, it will use the delta 0, which is used in the nil case of our fold, and it will need length axis many copies of our delta 1, which is used in each of the const cases, as well as the input list to produce a B. Again, the definition follows kind of relatively straightforwardly once you use kind of these new primitives in some way that we had to introduce in our system. And again, we can use this, for instance, an interspersing function. So this is quite neat. But we can also use other types to represent multiplicities. So one other interesting type would be the connatural numbers, which have not only zero successor, but also an infinity term, which is equal to itself, the successor of which is equal to itself. So we can again define such a exponentiation, now co-inductively, of course, because this is a co-inductive type. We can even, like as a nice syntactic sugar, have kind of function types which take in a connatural multiplicity, so A, and then m copies of A will be needed to produce a B, precisely if this dependent type here is inhabited. And using this, we can write quite nice functional programs. So, for instance, an iterate function, which takes in a linear function from A to A, and then it will need the input A infinitely many times to produce this iterated list. Okay, so this was programming in the system. Let's wrap up. I think you have some laksa to eat. You can tell I have a bit of FOMO. So here's Pierre-Martin Löw, Jean-Yves Gerard, and Kurt Gödel, how they would have maybe looked like when they had attended ICFP this year. So let's summarize quickly. So we've seen this recipe, so just a way to encode in cubic character this dialectical translation, giving us a linear typing discipline. And you can also carry this out in the other kind of theory, actually, without bags. I think what's neat about it is that linear elimination principles are just admissible. The caveat is we don't really have function types yet. I wrote the lollipop in some places, but it's really more syntactic sugar. There isn't really function types yet. But the upside is we can compute in our supplies, and thereby we can give precise types that we can't precisely type in other systems. And that was heavily influenced by a talk by Pierre-Marie Pedro last year in Tallinn at Transcendental Logic and Applications. And recently I've learned about some model construction by Robert Adke, which actually is very similar to this linear entailment. So this is kind of just on the semantical side. So one way to look at this construction is also that we use cubic character in some way to internalize some of the semantics of linear dependent type theory. And thereby we obtain this powerful theory. Okay, let me very quickly say what is next to be done. So I have an idea how to end linear function types, and also these productions are tedious to write by hand, so we can do this actually, I think, automatically. So there's a preprint with work in progress if you're interested. Let me just give huge thanks to Pierre-Marie and Valérie de Piper as well, who introduced me to Dialectica and many others I've talked to. And also, in particular, the SFP reviewers, who gave some really, really helpful feedback. Thanks a lot.
Excellent. Thank you so much, Maximilian. Let's we've got time for one question, I think. So, thank you so much, anyone in the room? Okay, I will ask a question. So, when you showed the safe head example, I, as a granule guy, immediately thought, well, I would give it the type with 0 to 1. I would use Granule's semi-ring of intervals over natural numbers, because then you can say it's 0 or 1 usage. And in Granule, you can combine semi-rings together, so you can do like intervals over semi-rings and things like that. So presumably, you can essentially have, like Granule, a kind of algebra of semi-rings quite easily then to generate new kinds of supply in your setup.
Yeah, sorry, I'm probably a bit delayed because I have to listen to the audio on YouTube. To answer your question, so absolutely. So in Granule, we would probably give an interval, we would use this either 0 or 1 times, which of course also works. But kind of this doesn't fully narrow down the space of possible programs. So in some way, it still allows a faulty implementation of safehead where you just always give back the y possibly. Sometimes at least. I think it would also be interesting to study different types to use for these exponentiations. So I think there's certainly room for affine systems as well in this setting, or to possibly also have some interval types by which we take exponentiations.
Yeah, cool. Great. Thanks very much. Okay, let's thank the speaker again.